Thank you guys for watching the second part to 36.1 exponential functions. We're going to look at the applications to exponential functions and real world scenarios, beginning with compound interest. Now, the compound interest formula is the following formula. A, which is the account balance, equals to P, the principal, the amount that we're going to start to invest or put into a savings account, multiplied with 1 plus R. R is our interest rate, normally given as a percentage, divided by N. N is going to be the compounding periods per year. Now all of this will be multiplied with, again, our P. So all of this gets multiplied with P, an T number of times N. So N times T number of times. And this is our compounding interest formula. Now, in this formula, the idea is that this value right here, again, this part right there, is the result of dividing the interest rate an n number of times, depending on how many times I'm going to compound it in a year. Now, most banks do things in a real world scenario, like actual real world. Mostly things do in a monthly basis. But we're going to do things differently. Also look at different possibilities and see what the price or the account balance, the accumulated balance of the account will be if we compound the same value at different compounding intervals. Okay, so let's look at an example of this and how we use this formula. So let's say that we have $10,000. We want to put those $10,000 into some kind of investment account, savings account, whatnot, for 5 years. That's going to pay out at a 1.332%. Okay. So the first thing I'm going to do is divide this number by 100. Divide this number by 100 and say that the value of R will be 0.0132. I need to remove again the percentage and write it as an actual decimal value without the percentage. So I divide that by 100 and I get that value. So to figure out the compound semi-annually, I'm simply going to get the $10,000 that I start off with. I'm going to add 1 plus, again, this interest rate, 0.0132. And I'm going to divide it by, in this situation, by 2, because I want this interest rate to be compounded twice in a year. So I'm going to divide this into 2 parts, one for the first time and an equal part for the second time. Now I want to multiply these $10,000 by this interest rate again for 5 years. So I'm going to raise this to the 5th power. So what this is going to do mathematically is that this interest rate is going to be multiplied by that. So I'll make like $1.32 the first time. So I'll make like $1.32, okay, the first time. And then that interest, that amount is going to also then be multiplied by the interest rate, and which is going to earn me a little bit more money. And then that amount with the interest rate is also going to be multiplied. So the interest is earning me interest. So it's not just multiplying it with like simple interest and this, all of this being multiplied with a rate all at one time, but the interest is also earning me interest. And that's what this formula is doing for us. Now this is going to happen again a total for 5 years, so I'm going to do this 5 times. But since each year is being compounded semi-annually, twice in a year, I'm earning interest every 6 months, so twice in 1 year. So I'm going to raise this and multiply the 5 with 2. Now plugging all of this into the calculator, which probably be the most beneficial and easiest thing to do, and not have to worry about trying to do this by hand, that's going to end up equaling to a total of $10,679.95. So this is the amount that this investment of $10,000 will be worth after 5 years. Now, if we look at the second example, same scenario, we want to still again keep the $10,000 at the same interest rate for 5 years, but this time we want to compound it quarterly. So we're going to have the value of n be 4. And that is not going to give much difference. Notice that compounding at different intervals doesn't make much of a difference in your overall balance. It's just less than $1, again, difference between compounding it 2 times and compounding it 4 times. Now, let's say we compound it 12 times, so that's a bigger number. It should make a huge difference, you would think, right? Because I'm doing it more times in a year. So that'll be 5 times 12, so that's like 70 times, 60 times that I would have to multiply 10,000 with. But I'm also dividing that value by 12. So this interest rate will be broken up into 12 equal pieces. So that's going to make that value smaller. So even though I do this more times, it doesn't give me, but because I'm also dividing it by 12, the interest rate by 12, it doesn't give me that much of a difference. It's only like a 80 cent, I'm sorry, like a 30-cent difference. I end up with $10,681.88. So 70-cent difference. And even if if I compound this interest on a daily basis 365 times, so 5 times 365, okay? The problem is again that I'm also doing that to the interest rate. So the interest rate is getting smaller. So this is the annual interest rate, the APR. The accumulated balance is not going to be that much different from 12. It's $10,682 with how many cents is that? Let me remember, 25 cents. So you see not much of a difference. But this is how you use that formula. And the amount that we have here, again, is the accumulated balance. Since we start off with $12,000, I'm sorry, $10,000, then it's easy to see what the interest rate that was earned. So in those 5 years, compounded four times on a quarterly basis, you earn an additional $681.11. When compounded 12 times on a monthly basis, it's $681.81, and here the interest that was earned is $682.25. Okay, so now let's say assume that the value of n, the compounding period is 1, so it's going to be compounded just once. Well, obviously that changes the formula. Dividing by this value by 1 is just going to be r, and then we'll multiplying t with 1 would just be t. So in those situations when there is no compounding period, aka the value of n is 1, the formula does change a bit. So let's go to the next page. Before going to this example, talking about compounding continuously, let's say that we just have normal exponential growth or exponential decay. In those scenarios, the formula does change. A will equal to a lowercase a times 1 plus r raised to the power of t. This formula here is more general. That can be applied in any scenario, not just compound interest, where the compounding period is 1, but in any scenario where we're increasing or decreasing by a specific percentage rate. Unlike lines that have a constant rate of change, these have a proportional rate of change. So the value between one y value to the next is growing or decreasing by the same scale factor, by the same proportional value. So like if we're doubling, let's say, the amount of ants in a colony, it doubles again every 6 months. So in 6 months, it's going to double. And then that amount, they're going to double in another 6 months. So we start off with 4, let's say 4,000. And in 6 months, it's going to be 8,000. And then those 8,000 are going to double. So it's going to become 16,000, and then those 16,000 are going to double in another 6 months, becoming again 32,000, and so on. So these increases, these rates of change, let me rephrase that. These increases are a percentage and not a rate of change. So for example, look at the example 7a. Let's say that Brooke starts her career at an annual salary of $32,000 each year. Now, each year after that, her salary is going to increase by 25%, meaning that the value of R is going to be 0.025. Notice that there's no compounding value. Okay, it's just going to go up by 2.5%. Now, what's her salary going to be after 30 years? So we use this formula where A is our initial value. So we start off with $32,000, increase it by 2.5%, not 25%, 2.5%, so 1.025, and do this for 30 years, so raise this to the 30th power. This is going to, again, calculate her yearly salary after those 30 years. And then by plugging it in, we get a total of $67,122.16. Okay, so the concept again is the same. So start off with her $32,000. She's going to earn 2.5%. So if I multiply this amount with 2.5%, or this number right there, that's going to tell me how much extra money she's going to earn the next year. Okay, so she'll earn the 32,000 plus that interest or that additional amount. Then that would be her new salary. And then I would do that again. I would add, multiply this percentage with that new value, the 32, and change the new value right there. And I would do that and multiply that with this value. And that would be again, 2 times. So I would do this again a total 28 more times. And I would end up again with this value. But the formula again automatically does this. So instead of doing it again in each individual intervals, and doing it one step at a time, I could do it all in one single step and figure out, again, the accumulated, in this case, her annual salary after those 30 years. So let's look at this example. So let's say that we have a math teacher who's a YouTuber. She has 140 subscribers. The number of subscribers is going to increase by 4%. So that means that the value of R will be 0.04. And how many subscribers she's going to have after 2 months. Now, notice that the unit of time is measured in months, but her percent increase is measured in intervals of weeks. So all we have to do is just simply convert this into weeks. Since 4 weeks make up a month, that would mean that 8 weeks would be 2 months. So we're going to use the number 8 for the value of t. So we start with 140 subscribers. It's going to increase by 4%. So 1 plus 0.04. And this automatically does 2 things. It adds the 1.4% and multiplies it with that, and then adds that 140 to that value. So that's why we have the 100%, the amount that we originally have, plus the additional 4%, 0.04. Now we're going to do this for a total of 2 months, which is 8 weeks, since this is growing per week. Since this value right here is growing per week, we need the time to also be measured in weeks. And then, well, this gives us a value that's approximately of 192 subscribers. So there's your answer. Okay, now since this formula again is mostly used again for more general stuff that has no compounding in it, we can also apply it for situations that are decreasing, for exponential decrease examples, like the next two. We have here that Kate drank an energy beverage with 150 milligrams of caffeine. Now each hour the amount of caffeine in her system is going to decrease by 12%. So since we're given a rate of decrease as a percentage, this is my hint again that we're using an exponential scenario. So the formula would be A times 1 plus R raised to the power of t. Now, since the rate is a decrease, that is going to change the value of R from a positive number to a negative number. So 12% would be 0.12, And because it's decreasing, we just simply use a negative value for that value of R. Now it's being, the decrease rate is measured in hours. So we need to make sure just that our time is also in hours, which it is. We want to know how much caffeine is going to be left of this 150 grams, how much of that's going to be left after 8 hours. So we have 1, and we're going to add a negative 0.12, which is the same thing as simply subtracting that value. So instead of adding a negative, I'm just going to subtract it and raise that to the power of 8. And then plugging this into the calculator, we end up with a total of 53.95 milligrams. So there's your answer. And let's look at one more example. We have here that last example that the half-life of mercury 197, that's just the name of the isotope, is 3 days. What that means is that we're going to decrease whatever amount of this isotope by 50%, so negative 0.50 every 3 days. Not per week, but per 3 days. So how much of this 50 grams are going to be left in 21 days? Since we're decreasing by 50% every 3 days, we're not going to raise this to the 21st power. So we have 50. Let me write this down first. Minus 50%, because that's half-life. Half-life means we're decreasing by 50%. So minus 0.50. But instead of raising this to the 21st power, okay, because we're going to see how much of this we have after 21 days, this would be true if this rate was happening per day, every 1 day. Then we would do it for 21 times. But because it's happening every 3 days, we're not going to take away 50%, a total of 21 days, only 7 times. Because in 3 days, it's going to decrease 21. So 0 days, there's no decrease. In 3 days, it's going to decrease 50%. And not until the next 3 days, which is on day 6, is it going to decrease another 50%. And then not until day 9 will it decrease another, again, 50%, and so on. So not until day 12, 15, 18, 21, 24, and 27 is it going to actually decrease again 50%. And since we want to get to 21 days, we don't need these. Okay, I don't know, I wrote those. That's a total of 7 days. 1, 2, 3, 4, 5, 6, and 7. Which basically is 21 divided by 3, 7. So we're only going to have to decrease again the 50 grams by 50% a total of 7 times. And then just plug it into the calculator. This isotope is going to decrease from 50 grams to 49 grams. 0.49 grams. So there's your answer. Now let's finally talk about continuous exponential growth or decay. Now, if things are growing continuously, so not in intervals of like a day, a week, a month, but like every single second, even smaller intervals of that, like always increasing or always decreasing, which is again considered continuously, then the formula is going to change. The formula for continuous growth or decay is A times E, Euler's number, that's 2.71, raised to the power of R and T. So in those situations, we have to use this formula instead of the previous formula. So for example, a biologist starts to a culture of a petri dish of 5,000 bacteria, and under ideal laboratory conditions, the population is going to grow continuously. So since we're given again that we have a continuous growth, we know that we have to use this formula. So again, context clues has to be provided to you to make sure that we understand there's a continuous growth of change. So at a rate of 40% per hour. So how many bacteria will be in the culture after 6 hours? So let's look at this value right here. So A will equal to 5,000. E 40%, so 0.40, and we're going to multiply it by 6. And then just simply using our calculator, we'll plug this into our calculator and we're going to end up with 6,356, I'm sorry, 6,356. So let's look at the second example. So an invasive species of fish is introduced to a lake starting with an estimated population of 300. Now with no natural predators, the population increases continuously at a rate of 22% per year. Now I know it's kind of, and I'm reading this, I know it's kind of weird that we're using the fact that it's always increasing, but then the rate is also measured in intervals of per year, like every 1 year. Okay, so it's kind of weird that we're saying that it's always this, in this situation, the fish population is always increasing, but it's going up at a rate of 22 percent. So out of every 100, we're going to have 22 new fish every single year. Okay, but again, it's still growing continuously. And because we're told that it's growing continuously, that in terms of formulas means that we need to use this formula instead of this formula. So again, here are the two options that we have in formulas. So we're going to use, like I mentioned, the first one. So we're not going to use that one. Okay. Let me use a red marker instead to exit out. So this one. So plugging in the information that we have, we know that we're going to start off with 300 fish. We're going to multiply it again by E, and that E is going to be raised to the 22%, which is 0.22, multiplied with 5 years. So 5. The time, again, has to match up again in the interval or the same units that the rate, the percentage, is increasing or decreasing, which is the reason why it's, again, specified that it's an increase in a rate of 22% per year. So if this was measured, let's say in months, we would just have to convert it into years. So it can match up to, again, to that unit there. And now, well, plugging this into our calculator, this is going to give us a value that is obviously going to be more than 300 because it's increasing. So it's 901. So 901 fish after 5 years. Let's now look at a situation where the rate is decreasing. So in example C here, we have a patient is given an injection that contains 800 milligrams of an antibiotic. Now the drug is metabolizing by the body, so it's going to decrease continuously at a rate of 30% per hour. Because it's decreasing continuously, that's just simply understanding that we have to use that formula here. So plugging in 800 for RA, E, since it's decreasing this time, just like the previous example, even though we're using a different formula, the idea that R is going to be a negative number. So negative 0.30. So we're going to use that number for R. And it's doing it in the units of hours, and we're measuring the time in hours. We don't have to do any conversions there. So plugging this into the calculator, this is going to be a total of 240.96 milligrams. Now pay attention to the number. Notice that we started off with 800, and now we have something smaller. Logically, it makes sense that we would have a smaller amount because we're decreasing. So if your answer doesn't make logical sense, one thing is occurring, okay? You're forgetting to change the value of R to a negative number if we're supposed to be decreasing. If you don't have a negative number there, it doesn't matter even on the other parts, even if you're using this formula here, the number will always end up being bigger than what you started off with. So had I used positive 0.30, then I would get a number that would be bigger than 800, and that logically doesn't make any sense because the value should be decreasing, it should be going down. So we look at the last example. We have this cobalt-60, that's the name of the radioactive isotope, used in a medical radiation therapy. It has an initial mass of 250 milligrams. Now, this isotope is going to decay continuously at a rate of 13.0% per year. Now, how much cobalt will remain after 3 years? Since it's a continuous decay, that tells us that the value of A will equal to A times E to the RT power. And the decay part means that this number is simply going to be a negative decimal value. So it's going to end up becoming that. So plugging in the initial value of 250 E, raising that to the negative 0.1304, and multiplying that by 3. Let me check that this is in years. Yep, it's in years, so I don't do any conversions. Like if it was in months, I would have to convert the 3 years into months. But I don't have that scenario, I don't have that situation. I can now plug this into my calculator, and we're going to get obviously a number that has to be smaller, okay? Since we're going down, it's a decay. It has to be 100 number smaller, and we get 169.06, which is smaller than 250 that we started off with. So this right here would be the amount of this cobalt 60 left after 3 years. Okay, now before we finish off, we did skip again a problem in the compounding interest part. So let's go back to that page. So in this page right here, let's talk about continuous compounding. Well, any scenario, even in compound interest, if it's continuously going to be compounded, again, if we have this word continuous, then the formula is going to be the same as the previous examples that we just did at the lighter examples. The only difference, instead of using the letter A, because we're talking about specifically about money here, I'm going to go back to this variable here, P. The rest of the formula stays the same. E will be raised to the R times T power. So all we're doing is just simply, for notation purposes, changing this variable from an A from the previous examples to the variable P. But it's the same formula. So whether you want to see it like this or you want to write it like this, it makes no difference. It's the same concept. So if I have these $10,000 that are going to be compounded at this rate of 13.2% continuously, again, compounded continuously, there's the word continuously. That means instead of this 1 plus R, I'm just going to use the letter E and raise that to my 0.0132 interest rate, my 1.32% interest rate for 5 years. And that's not going to make much of a difference if I do it an infinite number of times, if I compound it an infinite number of times, or 365 times. It's really, really close. It's $10,682.26. Only a cent difference. Okay, so it makes much difference in compounding it daily or compounding it continuously. So there you have it. So when it comes to, again, this last problem, just double check again, read the question carefully, see if it's using the word continuously. That's going to be your hint and your clue that you have to use this formula here, all right? That formula there. If it doesn't say continuously, then you'll have to use this version of the formula. If there's no compounding principle, like you're not compounding it multiple times in a year, then that means that the value of n is going to be 1. And with this number being 1 and that number being 1, well, it simplifies to this formula right there, okay? R divided by 1 and T multiplied by 1. So there you have it. Well, that concludes the second part to 6.1. I hope this video was helpful. And like always, I appreciate you watching and I hope you have a great day. Goodbye.